All right. So, in the previous lecture we talked about what can we do to make my rotor's induced power get minimized or optimized, and the trick was to make my I mean you can think of it actually the clue comes from my momentum theory. So, momentum theory power is ideal power, right. So, it is the minimum power that is theoretically possible. I mean power cannot go below that, right, and we see that theoretical power actually comes from inflow which is uniform. Okay. So, maybe somebody took that clue, if I somehow make my inflow uniform like momentum theory, in reality it is not uniform, I do something to make it uniform, maybe I will be able to minimize my power. So, they said okay, I will try hyperbolic twist. So, they explored that and they found yes, I mean my inflow tends to become uniform, and if it tends to become uniform it would actually have minimum profile power sorry minimum induced power rather. Okay. So, that was for the induced power part. We need to now also understand what can we do to minimize profile power. So, question that we need to answer today is how to reduce profile power. So, well, induced power minimization meant I have to do something to the induced velocity, okay, and that is what we did by changing the geometry. Now, in profile power I have to see my profile power comes from what? Drag. Okay. So, how do I minimize drag? For a given lift, because lift is fixed for me, right. I mean I have to still generate same amount of thrust that is required for my UAV to fly. So, what do I do to ensure that I mean I have same amount of lift, but minimum drag? Try to make more no, I mean where would you want your airfoil to operate? 75%. No, not maximize your L by D, right. I mean my lift is already fixed and I want to minimize D, which means L by D is maximum, right. Okay. So, that is the clue. So, always think I mean from very basic fundamental things. See, whenever you encounter a problem, the solution is typically very simple and trivial, very basic mechanics. Most source of the problems are incorrect mechanics, understanding the dynamics incorrectly. I can give you some simple examples actually, okay, maybe offline, okay, because some of that learning is related to the UAVs we have built. Okay. So, I do not want to put that in public domain, okay. But yeah, lot of learnings actually are from that, and it is mostly all very basic simple mechanics. So, when you encounter a challenge that something is not working correctly, okay, it is malfunctioning, it is not meeting the performance requirements, the reason for that is mostly very fundamental, in the sense that look at the basic dynamics, look at the basic aerodynamics. So, it is mostly getting the basics right what makes things work properly. Okay. Yeah. So, I will give you examples. Okay. So, let us start. So, here I mean we see I mean our objective is to minimize profile power, and again we thought okay, how do I minimize profile power? I have to ensure that my lift is maintained, because performance means I have to always balance my weight, whether it is a fixed wing, there is a rotary wing, any UAV I have to ensure that I get the same amount of thrust or lift which balances my weight. So, that is fixed for me already. Now, I want to minimize my drag. So, lift is fixed, minimize my drag means I am maximizing L by D, right, there is no other way. So, right. So, to do this, so now to ensure minimum profile power. So, my handwriting is readable, right, I mean you do not have any difficulty, and size is also okay, right, at the back. Okay, yeah. The rotor blade elements. So, because in blade element momentum theory we are looking at elements, blade elements. So, So, if you focus on one element, we can generalize it for all the elements basically. So, rotor blade elements must operate at their best L by D or C L by C D, right, which means if you take any airfoil or whatever airfoil that you have and draw the L by D graph for that, so C L by C D or L by D versus alpha, we will finally find I would want my airfoil to operate at this optimal angle of attack, which corresponds to maximum L by D. So, if alpha equals to alpha optimal for each blade element, then each section is operating at best L by D, okay, or best CL by CD. So, how do we ensure this? We go back and look at our DCT expression. So, how did my DCT look like? Half sigma CL alpha into theta r square minus lambda r into dr. So, that is my expression for DCT, and we are working with the rotor for which we have already optimized my induced power. Okay. So, I am already operating with my hyperbolically twisted rotor, the ideally twisted rotor. So, that my induced power is already minimized. On top of that, now I want to minimize my profile power also. Okay. So, we already have, we know, we will write here, for minimum induced power, we know theta is equals to theta tip by r, right. So, I can substitute that back in my DCT equation, use in DCT expression. So, what to have, we will get DCT equals to, and yes, and also lambda equals to, because the moment I used hyperbolic twist, my lambda is going to become uniform and it is going to become a constant value independent of my radial location. So, my DCT expression which I have here can be rewritten as half sigma CL alpha into theta tip by r minus lambda by r into r square dr. Okay. And this, if I see, is a, this term is basically my angle of attack alpha, right, because CL alpha into alpha is what I am doing, CL alpha into alpha r square dr. Okay. So, this alpha, let this alpha be equal to some alpha optimal. Right now, if you see this alpha, because theta tip is constant and lambda is constant, that means this thing is not constant, right, because there is a divided by r at the bottom. Okay. So, this alpha right now is not constant. Question is, what do we do to make alpha constant and be equal to this alpha optimum, which gives me my max L by D. Okay. So, right now if I plot this alpha as r tends to 0, your alpha will vary like a hyperbola equation, right, okay, where this is alpha tip, sorry, this is alpha versus r. Okay. So, this alpha if I plot, it will look like this, right. It is varying with distance, but I want it to become constant. So, we want to make alpha constant and to be equal to alpha optimal. So, from BEMT, we also have the expression of dCT equals to, well, using the momentum theory formula 4 lambda square r dr. Okay. So, the lambda expression can be written as, okay, using this expression, right. Okay. So, okay, maybe one, let me go back one more step. So, I can also, so this is one expression from my momentum theory, other expression which I wrote above is written like this, equal to half sigma CL alpha into alpha optimal. I am assuming it that this alpha optimal is somehow maintained constant, alpha optimal into r square dr. Okay. So, if I equate these two, I have this value of lambda equals to sigma r into CL alpha into this alpha optimal divided by 8. Okay. Right. So, we have used that expression and we are saying that, let us say, I mean, there is some alpha which is there and that alpha is somehow some alpha optimal, I end up getting this expression for lambda. Now, if I see this expression gives me that my lambda is actually, if I want alpha optimal to be constant, okay, this sigma into r should also be a constant, because if that is not constant, then my lambda will vary. So, this is constant if my sigma into r is also a constant. Okay. So, what could be a value of sigma r into constant or sigma r being equal to some constant? So, when r is equal to 1, sigma will equal to sigma tip. So, but what does this mean actually? Okay. So, this is fine. Okay. So, let us move forward. So, sigma r is some constant and is equal to some sigma tip, but what is the meaning of this? Now, if you recall, sigma is what? Sigma is NBC by pi capital R. So, NB is number of blades, does not change with radius, capital R is a constant, pi is constant. So, my C is what varies. So, if I want my sigma r to be constant, my NBC by pi r into r should be equal to some constant. So, which means that my CR has to be constant and equal to some C tip. What is my C? C is my chord, right, blade chord. All of you remember what is chord, right? Some of you look lost somewhere. I just thought I will check that we are still on planet Earth. Okay, so which means now I would want my C as a function of R to be C tip by, so actually these are small, I should not write them so big, C tip by small r. So, what is this? Or I can say this as sigma as a function of r, sigma tip by r. So, how does my chord vary now? What is this equation? Also hyperbola, right? Okay. So, it tells me that my chord distribution should also be hyperbolic if I want my angle of attack to be also made optimal and my inflow to be also uniform. So, this tells me that for an ideally twisted rotor, to ensure that the inflow and the sectional angle of attack is uniform or constant everywhere the chord distribution should be hyperbolic. Okay. So, hyperbolic chord or solidity means C as a function of r is given as C tip by r. Okay. So, this ensures that each section of blade operates at optimum lift to drag ratio. Okay, so, hyperbolic chord ensures this. So, how does hyperbolic chord distribution look like? So, if this is my C tip, my blade chord would look like this. Okay. So, once again you can imagine that is again an ideal chord distribution. Okay. So, we can call this as ideal chord. Yeah, top view. Yeah. So, if I cannot do that, what can I do actually? So, I can actually, I cannot use this hyperbolic thing, but I can use a linear taper, right. so which is form of approximation. So, I can have a linear taper with the same C tip whatever y this hyperbolic twist requirement gives me. So, clearly hyperbolic taper. Hyperbolic taper, just like hyperbolic twist, is not physically achievable. So, I will say that is not physical. But some taper which could be linear is beneficial for reducing profile power, right. And the combination of this ideal twist plus ideal taper would give me minimum power, both minimum profile power and minimum induced power. So, that kind of rotor is called optimum hovering rotor. So, we can say ideal twist plus ideal taper, it gives me optimum hovering rotor. So, again it is a concept, it is again an idea which allows us to come up with better design. It tells us, I mean, what would actually work for us if I try to design a rotor with minimum performance, minimum power consumption, in sense not minimum performance, minimum power consumption. I would ideally want to have some twist and some taper. So, you can understand that if I have my chord changing, my solidity is not a constant number, then solidity is a function of radial location, and based on that, I mean, one can actually define a geometric solidity, average solidity. So, I can take a mean chord and decide a solidity with that, or I can do some other things also, like there is something called thrust weighted solidity and power weighted solidity, which will not really go into, not that critical as such. But just for your information, the idea is that, I mean, I can actually try to find out a solidity for a rotor which will generate same thrust as the thrust of my this tapering rotor. So, then I mean it is, and then I find the corresponding mean solidity. So, one way is that, I mean, I find a mean value of my chord and say this is my mean solidity, which is my in some sense geometric mean solidity. Other way is that, I mean, I do my integration dCt with the chord distribution the way it is actually, find out my Ct, match this Ct with another rotor Ct with same radius, but a constant value of chord, and then I calculate the solidity from that. So, that solidity will be a thrust weighted solidity. So, I am just mentioning, it is not very important for us. So, I will not go into the details of this thing, but yeah. So, solidity would be variable, even for propellers you will see the chord is not constant, the propellers will always have some kind of tapering profile. So, you cannot just have a general purpose solidity, either you have to define a mean solidity or you have to define this thrust weighted solidity or something like that. So, I can do thrust weighted or power or torque weighted basically. So, I can match CQ or CT for two rotors and then say for a rotor with rectangular blade, this is the equivalent solidity, with all other profiles matching, my same CL alpha, same airfoil, same radius, same tip speed, everything else will match, only you will say there is a, my blade is replaced with a uniform chord. So, it will give you a equivalent value of chord for that, which matches the thrust of the my real rotor. So, So, taper does actually affect my performance. It tends to improve my figure of merit, because so before we move further ahead, I will just have one more comment on the taper part. Okay. So, effect of taper on performance. So, we try to look at in terms of my figure of merit versus CT. So, for a blade with rectangular profile, and a blade with tapered profile, well, it will not separate this fast. So, this is my tapered, and this is my rectangular blade. And this is my ideal figure of merit. So, tapered blade may have slightly higher, I mean of course, my drawing is slightly exaggerated, the difference may not be this kind of dramatic, okay. The actual difference may be much smaller, but tapered blade will have slightly better figure of merit. Question is why? An answer should be very obvious to you if you just simply look at the formula for figure of merit. It has induced power, well, top is actually ideal power, not just induced, which is ideal induced power. So, here I will say induced power, which means ideal power into kappa plus profile, right. And what is my taper doing? Reducing the profile power. Okay. So, if this guy gets reduced, my denominator is coming down. So, my figure of merit will automatically go up. Okay. So, it has slightly superior efficiency. If you want your rotor to be more efficient, you would want to minimize your profile power. I cannot minimize my induced power, I mean beyond a value, I mean I can do some twisting and so on and do something, but induced power is dependent on my thrust. Okay. So, if I demand a particular value of thrust, I cannot go beyond a certain level, but profile power I can minimize by doing taper, I can minimize by reducing my tip speed. Okay. So, making my rotor slower and slower, but I cannot make it too slow also. If I make it too slow, my thrust will start dropping and I will have to operate at higher angles of attack. If I operate at higher angles of attack, I will stall or I will run out of my control margins. Okay. So, these are some of the catch, but yes, if you want to design a quadcopter, also a multicopter, and you want it to fly for longer endurances or flight times, the trick is very simple. Okay. So, I want to make a quadcopter which is going to fly for 1.5 hours, for example, not very easy. Normally, your quadcopter fly for 30 minutes, right. So, what will you do? You will try to find the biggest possible propeller you can get with the direct drive motor system, okay, and make a very tiny fuselage and put long, okay, crazy arms and mount your motor propeller on that, okay. And you will find that, I mean my empty weight will be very, very low, and these rotors can be spun at very low RPMs, as low as possible, where their power loading is very high. Remember power loading? Okay. So, the power loading is very high and your power consumption will be very quite low actually, and you will be able to fly. So, I do not know, I mean somebody sent me a video of a solar powered UAV from the class, I do not know, somebody sent me that actually, okay. Some video where some guy actually has built again same logic they have applied and they put a big solar panel and he is saying it is flying directly, no battery required. Well, of course, no battery required, no payload also required. It is just a 4 rotors flying. So, that is okay. It is not sustainable idea. Solar power things will only work for fixed wing UAVs, but they are enormously long. There is a startup here called Maral Aerospace. Okay. They are trying to build a solar powered UAV. The problem is that they do not have good aeromechanics engineers, unfortunately. Okay. Yeah, so the first craft which they tried to fly, okay, the wing became like this. Okay. Because making a solar powered UAV means, I mean, your structural optimization has to be like super duper solid. Okay. That is the main player there actually. You have to make very lightweight structure which can sustain the load, and whatever you do, it will deform quite a bit actually. Okay. So, you have to do controls with deforming structure. Okay. So, this is a proper aeroelastic design challenge, and unfortunately in India there are not many good aeroelastic engineers actually. Okay. We are only handful people, okay, who understand aeroelasticity properly, and let us not call it fluid structure interaction, it is very demeaning for aeroelasticity. Okay. So, mostly people who work on fluid structure interaction, they work on cylinders in flow with springs supported, that is not an aeroelastic problem. Okay. Aeroelasticity is a far more serious problem actually, okay, and it is a very good domain to get expertise in, because there are not many people who have understanding of both fixed wing as well as rotary wing aeroelasticity. Rotary wing aeroelasticity is far more complex. If you understand that, fixed wing will not be very hard, but fixed wing has its own set of problems. Okay. They are different because it becomes more challenging for supersonic vehicles. Okay. So, estimating the flutter speed for a fighter plane, for example, okay, it is a very critical thing. So, I have mentioned a word called flutter. Okay. Are you familiar with this? What is it? Vibration?
The wings.
Well, you would have seen flags fluttering, right. Okay. So, your airplane wings, which may look very rigid and nice, can behave exactly like that. Okay. It will behave as if it is made of paper. Okay. And if you want to know about aeroelasticity more, take a note of watching a YouTube video on Tacoma Narrows Bridge collapse. Have you heard of this bridge? Yeah. Yes. So, some people have put this video with wrong caption saying that it is a resonance. It is not resonance. People who have put that, I mean, they have very poor understanding of mechanics. It is not resonance, it is a proper aeroelastic phenomena, it is flutter, and that bridge broke because of flutter. So, when you make a solar powered UAV, you have to be seriously worried about these things, very tricky problems to solve. Okay. Yeah, so one of my colleagues, I mean, I met in US, I mean, he was telling me about actually the person I am talking about is actually advisor of Professor I am really bad with names, Tanmay Mathur, yeah. Okay. So, his advisor was telling me that, I mean, he knows some people who are working on these HAPS UAVs, and you will not believe they talk about a phenomena called bird loading. So, what happens, I mean, these HAPS vehicles are flying nicely in sky, and sometimes, I mean, they get free passengers, birds come and sit. So, it changes the whole dynamics actually. So, he was saying, I mean, that they are so, I mean, marginal in terms of their weight, lifting capacity, strength, everything. If a bird sits on that, they are really worried, okay, I do not know if it is going to come back alive or not, something like that. So, that is the kind of challenge you are working with. So, people who think that, I mean, mechanics is not required because AI is there, no, it does not work like that anyway. Okay. So, right, so we got the idea that my profile power gets minimized, so I get better figure of merit, but that does not necessarily mean that it is always a better thing. If for a same radius, if I reduce my blade, I make it tapered, I am going to reduce my lifting area also. Okay. So, effectively same radius I make, and my root chord is same, and I am going to taper it, okay. Then my blade area is reduced. If my blade area is reduced, means my blade has to operate at higher angles of attack or higher speed, either way, right, one or two ways, which means I am going to maybe eat from my control margin. in terms of either RPM control or even for my pitch control. Okay. So, both ways I mean I am going to, so that those things we have to be wary of. Also if I have taper I mean my Reynolds number will come down. Okay. So some of these things will also have its role to play, and for small propellers, well small in the sense I mean propellers we are talking about, okay, like fixed propellers, you will always find some taper. Larger rotor blades, no taper. You look at blade of any helicopter, ALH, Black Hawk, right now I am working with this Cheetah Chetak helicopters. Okay. So all these blades are nice rectangular blade, all if at all I mean you may have some fancy tip shape, you may have some swept tip there, you may have a burp rotor design or a tail on tip design or whatever, some fancy design for noise reduction or some other small performance enhancements, but no taper. Why?
So mechanical design to make it a variable pitch will be complex.
No, but variable pitch I mean helicopters are variable pitch, what are you talking about? I am talking about helicopter rotors not being tapered. Well, I can think of two things. One thing is of course cost of manufacturing. Okay. So, manufacturing a blade. So, the question was why large rotor blades do not have and one was, well, you just look at this is my normal blade and other is my tapered blade. That may be there, but more than that I mean it is there are couple of tricky things. One is of course the manufacturing process becomes more complex. Okay. So, it may be more costly to make a tapered blade. Second is in rotor blades placing my CG, my sectional CG is very critical actually. And did I say very? I should say one more very actually. If you do not place it properly, it will have all kinds of problems actually. Okay. Lot of different problems. So that is again some form of aeroelastic consideration. So, because of those facts people stay away from that. So, the performance gain from tapering is not significant enough to outweigh the trade offs or the challenges involved with making a tapered blade, especially for large blades. Small blades I mean UAV scale blades you will still find tapered, there are blades which are available which have some taper, but it is still less common. Small propellers no problem, I mean propellers for eVTOLs or whatever I mean you are still going to what 50 inch 65 inches people are talking about, it is not too large. I am talking about blades which are 8 meter in radius, 5 meter, 4 meter in radius, 3 meter in radius, radius. So, it goes 6 meter diameter, right. So, we are beyond inches. So those blades I mean it is very hard to make tapered, okay. Will not find them tapered at all, they are all going to be rectangular. Okay. So, my gain is not that significant, but in small propellers I can make it easily tapered. So, there I mean I get benefit because small propellers profile power is high, okay, because they have high tip speed, lot of tip vortices. So, if I do tapering, vapouring and all my tip vortices will probably become less strong and I may have some benefits and so on, okay. That is the idea. Okay. So, now I will introduce one more very important concept. So, this and then we will look at the tip loss factor, okay, because right now my BEMT has given me a inflow which does not account for tip loss. Okay. It says my lift is maximum at the tip, which is not the case, lift has to come back to 0 at the tip because of the tip vortex. So, we will look at the tip vortex business and then we will study the performance part, helicopter performance, like we did fixed wing performance, we talked about endurance range. So, how do we analyze endurance range for rotary wing systems, be it a quadcopter, helicopter, single rotor, twin rotor, whatever. Okay. So, these are the main topics remaining, and the next homework assignment will require you to write a blade element momentum theory code. And this code is going to be a basic thing which, if you end up working more in aeromechanics or performance, it will be a very, very powerful tool. So, yeah. Okay, so now I will define this new thing called mean lift coefficient. It is again a concept. So, we say this is a very important parameter for both fixed pitch as well as variable pitch rotor designs. Okay. For rotor performance or rotor design or rotor analysis, we will say okay, rotor analysis, how and why, let us discuss that. It helps us define average operating state of the rotor. So, what is this average operating state? Okay, so, let us go back to my CT definition, half 0 to 1 sigma r square CL dr. Okay. So, that is my simple expression. Now, we said that, I mean, by doing some this ideal rotor and all, we could make our blade all sections of the blade operate at the optimal angle of attack, but in reality it will not be there. But what I can say is that I know that my angle of attack is different at every location of my blade, but I can define an average value of angle of attack, right. I can take all these values, take a mean of that. So, I know overall on an average what is my angle of attack. It is not a very great thing, but it is better than not having any clue what my angle of attack is. So, let us assume that all the airfoil sections on the blade operate at same CL, that is some CL equals to CL bar. So, this is like an average CL by combining all the CLs which are there. So, if I use that, my CT will become 1 sigma r square this CL bar into dr. So, I can take CL bar and sigma as constant. So, my integration is simply r square dr, which becomes 1 by 3. So, I would end up getting half CL bar sigma into 1 by, well, or sigma by 3 or whatever, yeah, I can write sigma by 3, or I can simply write this as CL bar sigma by 6, and I can flip it over and say my CL bar, this average value of lift coefficient, can be related to 6 CT over sigma. Okay. And what is the CT over sigma? CT over sigma. So, you remember what is my T by A? Disk loading, right. Okay. So, just like there is a disk loading, CT by sigma is called blade loading coefficient. There is not much space left there. So, what we found is that CL bar equals to 6 into CT by sigma, and we say CT by sigma is called blade loading coefficient. Okay. And there is also something called blade loading, just like there is disc loading, but we rarely ever use this term blade loading, which is T by area of the blades, which is T by NB R into C. Okay. So, this is called blade loading, but we rarely use that, but blade loading coefficient is an important parameter. Why? Because when I look at my CT, remember what kind of values we have in CT typically? Thrust coefficient. What are the numbers for CT typically? 0.004, 0.006, 0.008, maybe point. Okay. But then it is, and maybe 0.011, okay, or 0.015. But then I mean, it does not tell me what is the operating condition for my rotor, in the sense that my rotor, is my blade pitch very high, close to stall, or my blade pitch low or moderate or what, I do not know. So, it is unfair to just look at CT, or it is not very meaningful to just look at CT to decide, okay, I mean I am operating at high condition or low condition. Why? Because it does not account for my number of blades. How? You see, my CT has NB multiplied into it, right. Okay. So, if I have two bladed rotor, my CT is, let us say single blade is generating 0.004, okay, right. 2 blade 0.008, you will say, oh, this is fine, 0.008 is not very high value, but I put 4 blades. Now, it is 0.016, I make it 5 bladed, 0.020, it looks too high, right. Okay. You will think, oh, this is stalling blade, my rotor may be stalling, but it is not actually, because I have just put 5 blades for that. So, a more meaningful thing to look at is CT over sigma, because sigma tells me how much of blade is there in my design. So, CT over sigma is a more meaningful thing, and if you look at the range of that, independent of number of blades, it will always give you the same value, okay. And that is what relates to my mean value of lift coefficient. So, 6 CT over sigma will tell me my mean lift coefficient. If my mean lift coefficient is too high, it means my blades are being pushed towards stall. Okay. If it is too low, then I am very underloaded, okay. I have more margin. So, my CL is coming low, and I know what is my CL, what is CL to expect, right. So, let us see. So, let us assume CT is say 0.005, sigma is 0.1, typical nominal value. So, my CT over sigma becomes 0.05, and my CL bar is 6 times CT over sigma. So, it becomes 0.3, and this is fairly low value. I can even go beyond this actually. I can say this CL is actually equals to some CL alpha into alpha. So, I can use CL alpha to be 5.73, right. 0.3 divided by 5.73 is how much? How many radians, and convert that into degree? Can somebody do it and tell me? So, CL alpha I am using 5.73. So, my alpha would be 0.3 by 5.73. What is 0.5? Degrees did you convert? Multiplying with 180 by pi? This is radians. Multiply with 180 by pi. 3 degrees. Right. So, perfect. So, you see it is approximately 3 degrees. Makes sense, right. So, I am at low value of CL. Okay. So, my operating angle is also fairly low. If I now go to CT, which is 0.01, double of this, immediately you can see my angle of attack will double to 6 degrees, right. So, in some sense it is going to give you a sense of your operating state of the rotor, and we know CT could be. So, my CT, typical ballpark number for CT we often talk about is like this. Oh wait, why did I make it 0.005? That is too low. Yeah, that is why. I mean normally we have 0.05, not 0.005, or is it like that? 0.05 only, correct, yeah, because 0.006 and all, right. Yeah. Okay. So, actually yeah, so this is actually correct. So, this kind of range is meaningful for Ct by sigma, okay, not for Ct by sigma, that is correct, that is fine. Yeah. So, my CL bar 0.6 is typical for hover, and you should not go beyond CL bar of 1. So, your mean alpha bar, so this is actually alpha bar, not alpha, just because I am saying some kind of average state. So, this alpha bar should be typically of the order of 5 degree to 8 degree for hover. And you will not believe, I mean, people ignore these things and they end up crashing UAVs. Okay. These are very simple checks to do, right. I mean, how difficult it is. I know how much is my takeoff weight for my UAV, okay, and I know my density conditions and so on and so forth. So, I will get my Ct over sigma. I get my Ct over sigma, I get my CL bar, I will get my alpha bar, and if my alpha bar goes above 8-9 degrees, I am in trouble, okay, which means I mean my actuator may saturate, and this can happen very easily in high altitudes. Okay. So, this is very simple thing, right, okay, but very powerful information. Okay. So, again think always from very basic and simple things. Most problems have very simple and nice elegant solutions, they do not have complex solutions. So, do not think complicated stuff, think simple stuff. What is the very basic thing which is going wrong, which is causing some failure. Okay. Okay. So, just 1 or 2 more comments on this. So, mean lift coefficient is good overall indicator of average working state of rotor blades. So, it is indicative of how close rotor is to stall. Very important thing, especially when you operate at high altitudes. And it is also quite meaningful to analyze new rotor systems also, right. So, if let us say I am building a eVTOL system, right, okay, and my eVTOL craft requires certain thrust. Okay. So, I mean most eVTOLs will have 4 rotor, 6 rotor, 8 rotor, 10 rotor, whatever number of rotors. So, if I need to decide or design my rotor system for that, right. So, I have to see what kind of pitch, and this could be fixed pitch propellers, not necessarily variable pitch propellers. So, if it is a fixed pitch propeller, then I can easily set, okay. So, I know what is my takeoff weight approximately, and then I can see, okay, for my hover each rotor has to generate so much of thrust. If you have to generate so much of thrust, what is my Ct for my rotor, okay. What should be my sigma to ensure that my Ct over sigma is in the correct place, right. And if I want my Ct over sigma to be say slightly on the higher side like 0.12, I use this as a benchmark. I use this, I know my Ct, I will find my sigma. So, I know how many blades I should use, I can see what could be the disk loading I should have actually. So, you see I mean just by using some of these very basic numbers, I can without building anything, without thinking about anything, without going into a very sophisticated design software, I may have very clear idea of the power requirements, fairly decent idea about my battery power requirements, lot of things I can do just like that. Yeah. So, you see I mean these things are so powerful, I mean for you to design from a small UAV to a full scale eVTOL, okay, just by using these simple ideas. and that is how I mean I gave people to solve the Lilium jet problem. Okay. So, recently I was in I mean I told you right, I was in the Air Force event, and there I mean some company was coming and claiming, oh, we have, they put a big picture CAD model of their eVTOL system, and they are claiming, oh, we have started testing. I mean we would like to invite I mean Air Force to come and witness the testing, see this. I said, I mean why you do not show a video and testing does not mean I mean just doing a lift off. Okay. So, there is a company called well I will not name names. Okay. So, because this video is going to go on online. So, somebody sees and they may come and sue me. So, there is some company I mean based out of Hyderabad or somewhere, they are also trying to make eVTOLs. Okay. And they have made a really crazy fat looking multi-copter, really ugly looking multi-copter, again I will not name names, okay. And they are claiming they have made the eVTOL. Okay. So, now they can do whatever air ambulance, this thing, that thing, joke. Okay. So, I mean you are aware of this company called the foreign company Volocopters, right, the company which actually had this huge rotor with I mean sorry 26 rotors or 20 rotors on that. Okay. So, it is a really giant multi-copter, crazy multi-copter, and they got bankrupt. Okay. Another company Lilium Jet from Germany, they were making tall claims, got bankrupt. So, people I mean see they do not do basic mechanics, and they think I mean they are super smart to make an air taxi. See Joby and your Archer, these guys have slogged, they have worked on these concepts for almost a decade and a half. They started probably sometime in 2010s, 12s like that. Okay. So, almost last decade, okay, beginning of the last decade, okay. And now they have perfected things quite a bit actually. Okay. So, okay, fine. So, the next concept is on T plus factor. I will continue with that next class, because these VSSC guys are calling me. Okay. So, we will stop here and we will continue from here. Make sure you submit your homework assignment with Smita.